Hello everyone. So today we are going to understand a very important concept called eigenvalues of a matrix and how it helps us to understand nature of a matrix and work with matrix equations. So let us start. So I would like to start with the concept of matrix equations. So we know that we are always dealing with equations of the type Ax is equal to B. Okay. So now suppose you want to work with equations of the type Ax square x equals to B. Then you have to calculate A square. And then suppose you have to work with a cube x equals to b, then you have to calculate the cube of the matrix. Suppose you want to work with the 100th power of a, then you have to calculate the 100th power. So this is very challenging and we don't like this. Okay, so we want something very beautiful. What happens if there exists a non-zero vector x such that ax is equal to lambda x, where lambda can be a real number or lambda can be a complex number? What happens in a situation where when I multiply a with a vector x, I get lambda multiplied with the vector x. So the role of the matrix A is now taken up by this constant. It is always better to work with constant than to work with a matrix. So now understand that if you want to write a square x, that will be a into ax, that will be a lambda x. Now this lambda can come out because it is a constant. So that is lambda ax, which is lambda x, which is lambda square x. So a square x is as good as solving lambda square x. Similarly, if you look at a cube x, then a cube x is equal to a of a square x, and a square x is a of lambda square x. And now this lambda square can come out. This is lambda square into ax. So this is lambda square into lambda x, which is lambda cube x. So you can note that if we have this beautiful equation, then we can always have this kind of a situation, which is very convenient to work with. Okay. And also note that if x is equal to 0, then ax is equal to 0, which is equal to lambda times 0. So it is not actually helping us if x is equal to 0. So we are more interested in x not equals to 0. Okay. So now let's see. So let us start with the official definition. A vector, in fact, a non-zero vector x is said to be an eigenvector for a matrix A if ax is equal to lambda x. Okay, where lambda is a constant. Okay, now this lambda is called the eigenvalue associated with the eigenvector x. Okay, so if we are able to find a non-zero vector x such that ax is equal to lambda x, that x is called the eigenvector and this corresponding lambda is called the eigenvalue. Okay, now I can write this as ax minus lambda x is equal to the 0 matrix. So I can, write it as ax minus lambda ix is equal to 0, because if I multiply identity matrix with any other matrix, we get the same matrix. So it is going to be a minus lambda I x is equal to 0. Okay, this is my equation. Now we have already learned this, and mind it that we are doing everything with respect to square matrices over here. Okay, so we are doing with square matrices because now I'm going to come to the concept of determinant. So this is a homogeneous system of equation. Why this is called a homogeneous system of equation? Because the right hand side is equal to 0. So we know that zero vector is always a trivial solution to a homogeneous system of equations, but we know that here x is not equal to 0. So any system of equations, a homogeneous system of equations, has a non-zero solution if and only if the coefficient matrix has a determinant equal to 0. So that means determinant of a minus lambda I is equal to 0. So we have a definition for eigenvalue. So lambda is called an eigenvalue of matrix A if and only if determinant of a minus lambda I is equal to 0. The polynomial on the left hand side will be known as characteristic polynomial. Characteristic polynomial of A. Okay, and this equation is called characteristic equation. Characteristic equation, and the roots of this equation are called eigenvalues or latent values. Latent values is also a technical name for eigenvalues. So this is the definition of eigenvalues and eigenvectors. Now we will learn how to calculate eigenvalues and eigenvectors. So let's see some questions. Let us see. Now let us look at this matrix A. Find the real eigenvalues and associated eigenvectors of the following. So let me start with question number A. So my matrix is 1, 2, 3, 0. So if lambda is an eigenvalue, then determinant of a minus lambda I will be 0. Now what is a minus lambda I? It is 1, 2, 3, 0 minus lambda times I. So lambda 0, 0, lambda I is 1, 0, 0, 1. So a minus lambda I will be 1 minus lambda, 2 minus 0, 3 minus 0, 0 minus lambda. So what is determinant of A minus lambda I? Determinant of A minus lambda is 1 minus lambda minus 6. So this is minus lambda plus lambda square minus 6. So this is lambda square minus lambda minus 6. This is called the characteristic polynomial. Characteristic polynomial of A. Now I want to find out the roots of this because I want the determinant to be 0 for eigenvalues. So lambda square minus 3 lambda, we split the middle term. This is lambda, lambda minus 3 plus 2, lambda minus 3 equals to 0. So lambda plus 2, lambda minus 3 equals to 0. So lambda equals to 3 comma minus 2. Okay. So, okay. So these are the two values which I'm getting. So what are my eigenvalues? 3 and minus 2. Okay. So now let us try to find out an eigenvector. So let me try to find out the eigenvector x corresponding to lambda equals to 3. Okay. So I want to find out the eigenvector corresponding to lambda equal to 3. So what I should have, ax equals to lambda x. So what is my a? 1, 2, 3, 0. What is my x? Let it be x1, x2. It is a non-zero vector. Lambda x1, lambda x2. So I should have x1 plus 2x2, 3x1 plus 0x2 is equal to lambda x1, lambda x2. So x1 plus 2x2 is equal to lambda x1. Okay. And then I want 3x1 is equal to lambda x2. Okay. So from these two equations, if I will have to solve for x1 and x2. Now what is my lambda over here? My lambda is 3 over here. So let me put lambda equal to 3. Okay. So I am getting x1 equals to x2 from the second equation. Let me put in this first equation. So I am getting the first equation also as x1 plus 2x1 is equal to 3x1. So the only condition which I am getting is x1 is equal to x2. Okay. So what is my vector? My vector is x1, x2, and I can take x1 outside and I have 1, 1. So this is the eigenvector. So I can take x1 to be anything. I can take 1, 2, 3. So my eigenvector can be 1, 1. My eigenvector can be 2, 2, and so on. Okay. So let us look at the solution also. Yes. Okay. Now find out the eigenvector corresponding to lambda equals to minus 2. So that means my ax should be equal to minus 2x. So 1, 2, 3, 0. X is x1, x2, which is equal to minus 2x1 minus 2x2. So x1 plus 2x2 is minus 2x1, which means 3x1 is equal to 2x2, which means x2 is equal to 3 by 2 minus. And then I should have 3x2 is equal to minus 2x2, 3x1 is equal to minus 2x2. Okay. So therefore my vector x will be x1, x2, which is equal to x1 minus 3 by 2 x1. So you take x1 outside, you get 1 minus 3 by 2. And now x1 can be taken given any non-zero value because I need a non-zero vector. So this is how we calculate eigenvalues and associated eigenvectors. Let us try to do this for a 3 by 3 matrix. Okay. So let's try to do it for B, matrix B. So what is your matrix B? Matrix B is 5 minus 6 minus 6 minus 1 4 2 3 minus 6 minus 4. So your B minus lambda I would be 5 minus lambda minus 6 minus 6. Then it is minus 1 4 minus lambda 2 3 minus 6 minus 4 minus lambda. So I want the determinant to be 0. Okay. So I should be having 5 minus lambda, determinant 4 minus lambda 2 minus 6 minus 4 minus lambda. Then I should have plus 6. So I should have minus 1, 3, 2 minus 4 minus lambda. And then I should have minus 6, minus 1, 4 minus lambda, 3 minus 6. This should be equal to 0. So let us try to solve this. Okay. So I will be getting 5 minus lambda, 4 minus, so minus 4 minus lambda, 4 plus lambda plus 12 plus 6, 4 plus lambda minus 6, minus 6, 6 minus 12 plus 3 lambda. This should be equal to 0. So 5 minus lambda, this is lambda plus 4. This is a lambda minus 4, lambda plus 4. So lambda square minus 16 plus 12 plus 6, lambda minus 2 minus 6, 3 lambda minus 6 is equal to 0. So 5 minus lambda, lambda square minus 4 plus 6 lambda minus 2 minus 3 lambda plus 6 is equal to 0. So 5 minus lambda, lambda square minus 4 plus 6 minus 2 lambda plus 4 equals to 0. So 5 minus lambda, lambda square minus 4. So minus 12 lambda minus 2 equals to 0. So I will be having now 5 minus lambda, lambda square minus 4 is lambda minus 2, lambda plus 2, minus 12 lambda minus 2 equals to 0. So take lambda minus 2 be common. 5 minus lambda, okay, lambda plus 2 minus 12 equals to 0. So lambda minus 2, then you should have 5 lambda minus 2 lambda 3. So minus lambda square, then 5 lambda minus 2 lambda is 3 lambda, and then 10 minus 2 is equal to 0. So lambda minus 2, take the negative sign out. Lambda square minus 3 lambda plus 2 equals to 0. So minus lambda minus 2, lambda minus 1, lambda minus 2 equals to 0. So the eigenvalues are 2, 2, 1. Okay. So yes. Yeah. Okay. The value 2 is a repeated eigenvalue. So we have calculated the eigenvalues, and now let me calculate the eigenvectors. So let's calculate the eigenvector. So I'll calculate eigenvector for lambda equals to 1, and for lambda equals to 2, you people can try. So for lambda equals to 1, I want this bx to be lambda x. So I want bx to be x basically. So I want 5 minus 6 minus 6 minus 1 4 2 3 minus 6 minus 4 x1 x2 x3 is equal to x1 x2 x3. So I want 5x1 minus 6x2 minus 6x3 is equal to x1. Then I want minus x1 plus 4x2 plus 2x3 is equal to x2. Then I want 3x1 minus 6x2 minus 4x3 is equal to x3. So let's try to write the first equation. So it is 4x1 minus 6x2 minus 6x3 is equal to 0. So that is 2x1 minus 3x2 minus 3x3 is equal to 0. This is the first equation. In the second one, it is minus x1 plus 3x2 plus 2x3 is equal to 0. And in this one, 3x1 minus 6x2 minus 5x3 is equal to 0. So basically now you have three equations. So you have to solve it like this. 2 minus 3 minus 3. Then I have a minus 1, 3, 2. And then I have 3 minus 6 minus 5. x1, x2, x3 is equal to 0, 0, 0. So let us try to convert this into a beautiful form, that is a triangular form. So first let me just recheck the equations. Okay. So let me make R2 goes to R2 plus half of R1, and then R3 goes to R3 minus 3 by 2 of R1. Okay. So 2 minus 3 minus 3 minus 1 plus half of 2, 0. 3 plus half of minus 3, 3 by 2. 2 plus half of minus 3 by 2. So that is half. So because 2 minus 3 by 2 is half. Okay. Then 3 minus 3 by 2 of 2, 0. Minus 6 minus 3 by 2 of minus 3. So it is going to be minus 6 plus 9 by 2. So minus 15. So minus 3 by 2. Minus 12 plus 9. So minus 3 by 2. And then it is R3. So minus 5 plus minus 5 minus 3 by 2 into minus 3. So minus 5 plus 9 by 2. So that is minus half. Okay. So minus 5 plus 3 by 2. Okay. So are we subtracting? Yes. So minus 3 by 2. So plus 9 by 2. And again plus 9 by 2. And then 3. Okay. So this is x1, x2, x3 is equal to 0, 0, 0. Okay. Now what I can do, I can actually make R3 goes to R3 plus R2. So it will be 2 minus 3 minus 3, 0, 3 by 2 half, 0, 0, 0. x1, x2, x3 is equal to 0, 0, 0. Okay. So what I can do is now that I can use the first equation as the second equation as 3 by 2 x2 plus half x3 is equal to 0. So 3x2 is equal to minus x3. So x3 is equal to minus 3x2. Okay, and now you can put this in the first equation. So the first equation is 2x3, 2x1 minus 3x2 plus minus 3x3 is equal to 0. So that is going to be, so x3 is minus 3x2. So 2x1 minus 3x2 plus 9x2 is equal to 0. So 2x1 is equal to minus 6x2. And so x1 is also minus 3x2. So your vector x1, x2, x3 is now coming out as, you can take x2 common. So x1 is minus 3x2. So minus 3, x2 is just 1, and x3 is minus 3x2. So this is my eigenvector. I can now give a non-zero value to x2 and solve. So you just have to go by the definition of an eigenvector. So what is an eigenvector? An eigenvector for a square matrix A is a non-zero vector x such that ax is equal to lambda x, where lambda can be a real number or a complex number also in case of complex matrices. Now this lambda is known as the corresponding eigenvector with respect to the eigenvalue with respect to the eigenvector x. Okay. So if we have a 3 by 3 matrix, we are going to get 3 eigenvalues. They can be repeated or they can be different. Now, why only 3 eigenvalues for a 3 by 3 matrix? Because we are going to get a polynomial of a minus lambda I, which is going to be of degree n, which is equal to the order of the matrix. So this is all about how to solve eigenvalues and eigenvectors of a matrix and why they are useful. That I have already told you. They help us a lot in calculations, and later on we will be dealing with topics like diagonalization of a matrix. There it will be very important. Thank you very much.